All right. Hello and welcome everybody to the industry track here at TIPE 2023. My name is Stephanie Hendrickson. I'm the track leader, and I'm going to bring our first presentation up on the stage. Our first speaker today is Pam Waterman. She is a senior applications engineer for 3D printing at PADT, and she's going to be talking about 3D printing for space applications. So Pam, I'm inviting you on stage. Go ahead and enable your microphone and camera, and we'll get started.
Okay, great. Thank you, Stephanie. Hey, everyone. It's a little tough following up on those great opening talks, all that information, and that amazing keynote speaker. But as Stephanie said, I think with all the possibilities open to 3D printing, starting off with 3D printing in space is a pretty good idea. I'm Pam Waterman. As she said, I'm a 3D printing application engineer at PADT, that's Phoenix Analysis and Design Technologies, in Phoenix, Arizona, in the States. In the work that I do, I'm primarily working with polymers, but in my first career, I was an astronomy major. I have a degree in astrophysics and one in radio astronomy. And after that, uh, my first love really was space exploration. So I thought I was going to be an astronaut. However, I ended up discovering microwave engineering, antenna design, and eventually 3D printing. And I'm really glad that that's the path that I ended up taking. So I'm going to share my screen now and let you see these slides that I have. And go into presentation mode. Okay, so I was introduced to 3D printing in 1996 when everything was still called rapid prototyping. Of course, prototyping is still important for many additive technologies. But today I want to share with you an overview of dozens of ways that 3D printed parts are launching, orbiting, and operating in space. Real materials on real missions. When I started to pull together this information a few months ago, the first thing that struck me was discovering there's a new buzzword that captures some of the excitement and activity surrounding today's world of space exploration and operations. It's called the new space industry, and even a quick search will show it's been attracting interest across a wide range of supporting fields. These include hardware for the launch vehicles, from engines to fuel to the seats inside a capsule, satellites, both large and small, like CubeSats, the operators and the ground control experts, the software needed to run everything, and the experts and the programs that analyze the data involved, and at a deeper level, the components and their materials that must survive and function at every step of the way. So, how does 3D printing fit into this new space industry? And why is it such a good fit? Why does it rock for rockets? And how is it that 3D printed parts started flying in space almost 10 years ago? Many of the features that make 3D printing or additive manufacturing attractive in other applications are even more important for working with space. My first thought was having the chance to design and produce a part with organic, conformal shapes and interior geometry can improve the fundamental performance of a mechanical part. For designs that truly take advantage of additive, these shapes simply couldn't be made as a single piece any other way. Second, that single piece description is quite important. Additive lets you consolidate what might have been multiple parts into one, possibly smaller component, which leads to the third point, material savings. Many parts destined for assembly into a rocket are made from expensive materials such as titanium, so only printing with the bare minimum of raw material is quite attractive. And there's more. Additive designs are highly supportive of parts that are anything but solid, which would be the usual approach for something made from casting or machining. Here's a simple example of a bracket that has been optimized for the minimal structure while safely performing as needed. Since every kilogram of payload adds to the demand on the rocket booster, weight savings means either cost savings or more payload for the same thrust. Combining parts and functions in a single piece eliminates assembly steps. Each bolt adds weight, and every weld is a potential point of failure. This is huge. Number 6, in the world of metals, or at least primarily for metals for now, Blended materials and new alloys are possible, which leads to improved material properties such as improved strength or heat tolerance. And lastly, just being able to print and finish a part in days or weeks instead of months or even years means designers can iterate, test, and redesign in a greatly compressed time frame compared to the traditional methods of past decades. I'm going to start describing polymer or plastic parts that have already been used for space applications starting in 2013, such as on board the Northrop Grumman and Antares vehicles that were typically used for resupplying the International Space Station. These may not seem very exciting, but are definitely important as they contribute to weight savings and are easily customized. These include custom housings for electronics and avionics, brackets and clips to hold all sorts of wires and cables firmly in place, and structures that serve as connectors, large and small. A good question to start with is, when are polymers used instead of metals? When the components need some or all of the following properties. You need them to not bend, melt, or get brittle if it's really hot or cold. They're very strong for a small amount of material or like a thin wall. There's a chance that adding carbon particles will make it so they don't attract static charges that could short out electronics. You might need plastic to not give off any kind of volatile particles that could contaminate high voltage equipment or optical surfaces. The materials need to be chemically resistant during manufacturing and operations so they don't react to solvents or oils. And being flame retardant is definitely important. A note about the low outgassing requirement. I found out that in the Apollo 8 mission around the moon, the silicon rubber seals around the large observation window outgassed when they were under vacuum, and they temporarily clouded the view until they could be cleaned off. The most commonly used 3D printing approach for space polymers uses a spool of plastic filament which gets melted and deposited through a fine nozzle. Parts are often built with a secondary support material to keep the overhangs and holes from collapsing, and the support can be breakaway or soluble. I've found two types of materials primarily used for space, although I'll mention some others in a bit in the polymer world and related. Ultim 9085 filament, produced from a resin made by a company called Sabic, and Antero ESD, a carbon nanotube filled PEC material that's polyethyl ketone, both developed by the 3D printer manufacturer Stratasys. Both can withstand fairly high temperatures without melting, over 300 degrees Fahrenheit, and parts made with these materials won't expand or contract greatly when exposed to extremes of hot and cold temperatures. In addition, Antero ESD has properties that are good both electrically and chemically. So here's the first of four cool applications I think about of polymer parts in space. An unusual project that has used multiple Ultim 9085 parts comes from MIT and NASA Ames Research Center. It's called SPHERES, which stands for Synchronized Position, Hold, Engage, Reorient Experimental Satellites. Various iterations of these colorful nanosatellites that I think look like volleyball-sized dice have floated inside the ISS since 2006 with an initial goal of testing algorithms and sensors that have to do with docking and weightlessness. Later versions, from what I've found starting in 2013 and perhaps again after that, I'm not quite sure, did contain Ultim 9085 parts. By the way, in general, when you see a date I've listed on these slides, it's what I've found online about the use of 3D printing. I'm sure these groups and companies were working with 3D printing for years before, but I wanted to stick with what's publicly listed. Moving ahead a few years, based on previous experience, NASA realized it needed to work with a filament that was electrostatic dissipative, had ESD properties, and also displayed great chemical, mechanical, and flame smoke toxicity, that's FST if you see it, behavior. Since Stratasys had already developed this basic PEKK filament they called Antero, they worked with NASA Goddard Space Flight Center to develop a version filled with chopped carbon fibers and added ESD properties. NASA printed Antero ESD brackets, you see in this red circle, to guide and separate fiber optic cables inside a satellite that they launched in 2018. The third application I found was the Mini USO Extreme Universe Space Observatory, launched in 2020. This unit is one element of a multi-component system now flying on the ISS to help study terrestrial and cosmic UV emissions. In the center of the photo, in the red circle, is a section housing photomultiplier detectors held by custom-designed Ultim 9085 brackets. The engineers said 3D printing allowed them to make last-minute changes before committing to a final design and also lowered the weight of the detector's framework. Here's a couple of close-ups of those brackets, again in the red, and at the top with an extra cover. And lastly, for polymers, I have to admit this is my favorite application, although I am a little biased. I'm also excited Stephanie showed this picture too. My company, PADT, was involved with Stratasys and Lockheed Martin in the development of that special Antero ESD material. This is what you see used here in the black in the center, forming the actual docking hatch cover of the Orion capsule launched just this past November on the Artemis 1 mission. 6 3D printed segments fit together to make this 1-meter diameter hatch cover, and it faced open space. The picture here is a fake with a photo of the Earth, but for real, it was an exterior component, not just something on the inside, and I think that's really awesome. Okay, moving on to metals. The possibilities found within these materials are taking 3D printing to a whole new level of space applications. They're also compressing development and production timeframes in ways that would have been hard to imagine decades ago. All of the factors we talked about at the beginning about why you would 3D print for space hold particularly true with metals. You can appreciate the challenges involved in building traditional rockets. It typically takes years to build, 40% of the cost is in the engine, and to produce combustion chambers, you would cast and forge separate components, weld them together, and then do time-consuming, labor-intensive machining to add any kind of cooling channels around them. If you could cut down that time and cost and simultaneously improve the performance, you could support far more frequent launches, especially with reusable components. I'm also going to mention one other metal application that particularly interests me in a bit, that of 3D printing antennas. First, talking about metals in general, the important properties for space operations are similar to those for polymers: maintaining strength at high and low temperatures, saving weight, and being chemically resistant. Titanium, being inherently lightweight, has been a common metal of choice, but nickel alloys, which are always good for avoiding corrosion, aluminums, and more recently copper alloys, are also coming more and more into use as researchers figure out just how to make them printable. The most common additive technology for metals is laser powder bed fusion, where fine layer powdered metal is fused layer by layer using one or more lasers. However, for space applications, both directed energy deposition and wire arc melting have become extremely important ways to work with metals. This image from NASA shows a copper combustion chamber built with powder bed fusion that's part of a very current, low-cost, upper-stage rocket development project. The part was printed from an alloy called GR Copper 84, created by materials scientists at NASA's Glenn Research Center in Cleveland, Ohio. Where the ring of holes are visible at the bottom, these are the openings to more than 200 intricate channels built into the inner and outer walls, providing efficient gas circulation. Here's another important application from NASA that Stephanie also referred to. It involves the Perseverance rover on Mars, which featured a total of 11 3D printed parts. 5 parts were in the Pixel, which is short for Planetary Instrument for X-ray Lithochemistry, a device that analyzes rock surfaces for microbial life. It includes a 2-piece titanium shell, a mounting frame, and 2 support struts, all 3D printed. It had to be lightweight because it was mounted at the end of a 7-foot-long robotic arm. Then Perseverance's 6 other 3D printed parts are in an instrument called the Mars Oxygen In Situ Resource Utilization Experiment, otherwise known as MOXIE. This device was designed to test technology that in the future could produce industrial quantities of oxygen to create rocket propellant, like right on Mars. To do so, it will heat up Martian air to nearly 1,500 degrees. So this unit needed 6 nickel alloy heat exchangers to protect its other components from the high temperatures. I'm sure you know that along with NASA, there's a growing list of commercial companies that are tackling many aspects of this new space industry. This is a list of some of the more prominent ones known to be working with 3D printed metal components. I know I've missed many. I mean, I really know that because every time I thought I was finished with this talk, I found another one. But these have made the news quite a bit. In the interest of time, I'm just going to highlight 5 of them, but of course, feel free to mention other companies and applications in the chat. Aerojet Rocketdyne is a long-established company in the space industry, having supplied, among other things, the main rocket engines for the space shuttle. They've been working with additive for more than 2 decades, and that R&D has sure paid off. In 2016, they hot-fired the most complex yet 3D printed nickel alloy main injector system. In 2017 came the largest copper alloy thrust chamber ever built with 3D printing. And now, for the Artemis Orion system, they provided multiple reaction control systems, 12 on the main Space Launch System and 12 on the Orion spacecraft itself. That latter is in the green circles in the picture. The company uses a number of different metal powder printers and variations on powder bed technology. Blue Origin has certainly gotten a lot of publicity from flights with citizen astronauts, including my early career inspiration, William Shatner, but it's their technology that really shines. I was just at a conference last week that discussed Blue Origin's New Shepard reusable rocket and learned that its BE-3 engine includes more than 400 3D printed parts. And the oxygen boost pump alone on the BE-4 engine version features an aluminum housing 3D printed in one piece, along with all stages of the hydraulic turbine. Both are printed from Monel, a nickel alloy. They say the time savings alone has compressed the build cycle from 1 year to 3 months. Relativity Space, with its Terran 1 rocket, was founded in 2015 and is now famous for using its Stargate printer, shown in the upper picture, their own version of a robotic wire arc melting system, to create the huge rocket fuel tanks shown here. Over 85% of the rocket by mass is 3D printed, using multiple alloys they developed themselves. Relativity Space says 3D printing made it possible to use 100 times fewer parts compared to traditional launch vehicles, which helps them build a rocket in 60 days instead of 2 years. Also, as I mentioned before, by reducing the complexity, the chance of failure is also reduced. Terran 1 is currently scheduled for its first launch next month. And Rocket Lab, founded back in 2006 in New Zealand and now headquartered in California, developed the first 3D printed electric pump engine whose internal geometry promotes superior mixing. They customized electron beam melting printers, EBMs, to do this, producing prop valves, injectors, pumps, and engine chambers. And they have already completed 32 launches, deploying 152 small satellites, starting in 2013. Launches now occur pretty much every month, and each rocket uses 9 of the 3D printed engines. With all the previous launches originating in New Zealand, the company's next launch, set for this afternoon, will be from US soil. Okay, you may have noticed that the years 2013, 2014, and 15 saw intense activity from these new space industry companies. But I should note that SpaceX seems like the grandfather of them all. Founded back in 2002, its current and former engineers have certainly helped bring additive to mainstream space applications across many other companies. In 2011, SpaceX printed the body of an oxidizer valve for the Falcon 9 Merlin 1D engine, and in 2013, the company printed the engine chamber of its Super Draco thrusters. Both of these use DMLS metal printers. More recently, SpaceX has signed on with Velo 3D to print metal parts with even more demanding requirements. Switching away from rockets, but also destined for space onboard satellites, are the custom, highly compact microwave and millimeter wave antennas 3D printed by Optisys. They use metal alloys to create custom antenna components that would otherwise be very difficult and complex to assemble. Here you can see some of the base structure is an open grid. These sections are necessary in laser powder bed printing to serve as thermal paths during printing, but they also serve as permanent structures, useful for both mechanical and thermal properties. You can just imagine that the loose powder that isn't solidified by the laser just blows out from all those open areas. Rockets and antennas aren't the only space-related components in the 3D printing world. Via Space, founded in 2017, is producing rocket engines actually fueled with 3D printed grains made from recycled thermoplastic material. I don't know the exact material involved, would love to find out if anyone knows. That solid thermoplastic becomes high-energy fuel when combined with liquid oxidizer and ignited. The first launch using this rocket for launching satellites was in 2022. More launches are scheduled this year. Then, back to NASA again, I found an article about this 3D printed chainmail sort of looking fabric. It's smooth and reflective on one side, but heat and light absorptive on the other. It looks kind of like a mesh of loops. It's being proposed as a covering on antennas or even the outer layer of spacesuits to help regulate temperature. Lastly, I had to consider truly 3D printing in space because that too has been done for quite a while. The first experiment was in 2014 on the space station using a filament type printer produced by a company cleverly called Made in Space, now owned by Redwire. They wanted to test the effects of microgravity on the printing process. The final parts, like a wrench, as analyzed when flown back to Earth, showed no measurably different properties from those made in Earth based printers, which I think is both cool and hopeful for future use. Other work done since then by Redwire has included using a stereolithography printer to cure a ceramic filled resin, done in 2020, experiments in bioprinting tissue, and most recently, this past December, using low density polyethylene filament to make a series of small but thick discs. These could be slipped inside a special fabric vest to make it shield against radiation. Okay, since I'm getting short on time, I'll just mention a cool company called Fabrasonic, founded in 2011. It's cool not only because of how it uses something called ultrasonic consolidation to bond thin layers of metal without melting, but also because it's based on technology invented and patented by a woman named Dawn White in 1999 when she formed Solidica in Ann Arbor, Michigan. So, way back then, women were working hard in 3D printing. My last note has to do with the all important topic of food. In 2013, Systems and Materials Research Corporation got a NASA grant to figure out 3D printing pizza crust and toppings. And if anyone has an update on that, I'd love to hear it. So here's my parting shot, a view of the Orion capsule actually in space last month. Just around the right-hand edge is the hatch printed in Ontario ESD. My thanks go to PADT and Women in 3D Printing for inviting me to speak and all their support. Thank you for listening, and I'm happy to answer questions.
All right, Pam, thank you. That was awesome. One note from the chat, if you do want to learn more about food in space, Rachel Enfield is going to be talking about that at 9 p.m. Eastern. So you get an update there.
Great. Okay.
All right, looking for questions here. There is a dedicated Q&A tab, so if you can use that for your questions, I'm going to try and spot what I see in the chat here. Do 3D printers in space have to be stabilized somehow? How do they regulate temperature and humidity during printing? Can you speak to that, Pam?
I would say absolutely yes, because that's important on Earth, and it would be even more so up there. I'm sure it's an extra tricky job to stabilize the external temperature as well as the internal temperature of the printer. And I would think that they have it bolted down or else working with a gyroscope mechanism to make sure that it stays level. Because, we think it's tricky here on Earth having a level bed. That would definitely be critical there.
Yeah, added challenges for sure. All right. That's all that I'm seeing in the chat right now, but maybe just while I have you, what are there ways that innovation for space transfers back to Earth? Like, are there applications for Antero on the Earth's surface and things like that? Did you find connections going that way?
Yeah, it is, I think, the legacy of NASA that a lot of technology that was developed for space is brought back down here. Uh, I know way back, freeze-dried food was originally developed for astronauts, and now it's something here. So in the 3D printing, the fact that we are working hard to make things lightweight will transfer down and has already, say, in aerospace. There's the famous GE fuel injector that's 3D printed in metal. It's more efficient and it's lightweight. And years ago, they already passed 35,000 of those printed and in flight. By the same token, when you think of all the automotive applications right now, particularly for EVs, lightweight is important because the battery has to provide enough power, and the weight in some ways I think is more important for those vehicles than for a traditional combustion vehicle. So I would say the weight savings, and then the fact that we're moving more towards manufacturing, doing these faster, is going to allow it to go into fields where making just one or two wouldn't be economically viable.
All right, we've got a couple of things that came in through the Q&A here. Um, Do you see applications for UV cured polymers in space? So things that you would use in DLP or SLA processes?
I think it's going to be a little trickier because anytime you're dealing with a liquid and a resin, that is a challenge. But I have seen already, didn't get to mention that they are working with ceramics in a slurry. So that's in a liquid form. And from what I've seen, as long as it's in a sealed chamber, they can work with that where you're curing it in terms of the original process. And then while it's in that same sealed system, if it then can do the final UV curing, which is typical for a DLP kind of part, then when you took it out, it wouldn't have a risk of the fluid flowing elsewhere. And I would imagine with other fuels and liquids they work with, as long as you have a sealed environment from your storage unit into what you're filling, it would be possible.
All right. Can you comment at all on the qualification and approval process for additively manufactured parts? How much of the process has been figured out and how much is still being developed on the fly?
Oh, that's a great question, and I'm glad you and I are going to get to talk about that in just about an hour. Qualifying parts, it's a big step up from a prototyping or a onesie twosie or something that's a non-critical application to something which truly is critical and has to have a long life. The talk this morning that mentioned standards, that's one of the important things. And inspection, qualification procedures are really being looked at and improved upon and documented. So I think there's a lot of attention being paid to that right now. In parallel, again, the aerospace and the automotive seem to lead a lot of things, but also I wouldn't overlook what's being done in the medical world. They have extremely stringent standards, always have, and I think we can learn from that too. Whether it's, do you need to scan a part? Do you need to do destructive testing, non-destructive testing? How do you track the material from the very beginning and, have traceability for it? All of those pieces are starting to be addressed, which wasn't really required when it was just about prototyping.
All right, we can do one more quick one here. Um, so we talked a little bit about the challenge of like keeping the printer level in space. What specific challenges do you see with working with particles in zero gravity? So more of the material issue.
Sure. That one I personally think is going to be the hardest because any particulate matter is definitely a challenge because of how it could contaminate the operation of any of the other equipment, as well as just something like a breathing issue when you're in space in a vacuum. I have no doubt at some point that will be dealt with, but it might require like a specialized chamber that is attached to part of the space shuttle, the space station, or when it's finally down on the moon. Uh, with gravity being different or non-existent, yeah, I would say that is definitely a challenge.
All right. I will ask you one more because we do have a few minutes here.
Okay.
Could you comment on printing on the moon or on Mars for building habitats?
I'm really excited how that's coming along. There are so many companies that are addressing 3D printing with concrete here on Earth, and so many of those are looking ahead to, okay, how do we source the material on the moon, on Mars? What is the soil, the dirt made up of? Is there anything in there that wouldn't be conducive to mixing? How do we get the water to mix with that? But I can't see bringing our own materials, so I do think that that's going to be a critical challenge. But again, will probably be met just because of so much progress that's already being made here. Whether it's how you get the material to flow, how do you keep it at the right temperature? We had a 3D printed house done here in Arizona purposely in the summer 2 years ago. Keeping that cool and not hardening before it was where it was supposed to be was an interesting challenge, but they figured out ways to do with it.
All right, we will leave it there. You can see Pam on the panel that's coming up in about half an hour. Thank you so much for presenting.
You're very welcome. It's a great topic. Thank you for asking me.